Industrial plants need steam for heating and other processes. Boilers are commonly used to provide this steam. You may be called on to operate the boilers in your plant. The first step towards safe and productive operation of boilers is a good working knowledge of boiler fundamentals. The function of boilers is to produce steam. Steam is produced by heating water to its boiling point. When water reaches its boiling point, it changes from a liquid to a vapor. It's this vapor that we call steam. So basically, to produce steam, you need two things: water and heat. To generate the heat needed for steam production, boilers rely on the process of combustion. That is, they burn fuel to provide the heat required. In simple terms, there are four requirements for combustion, which we'll illustrate on a combustion triangle. One requirement is fuel. Most boilers burn oil, natural gas, or coal. The second requirement is air. More specifically, air contains the oxygen needed for combustion. The third requirement is heat. Heat is required to raise the temperature of the fuel-air mixture to a point where a chemical reaction or ignition takes place. The chemical reaction is the fourth requirement. If any one of the requirements is missing, combustion will not occur. The two requirements for steam production are water and heat. The heat's provided by combustion. Boilers are designed to allow the requirements for steam production and combustion to come together. Let's see how by looking at a boiler's basic operating principles. We'll assemble a simplified boiler. This is a container or shell. With water in it, the water takes care of one of the requirements for steam. We'll also add a pipe to provide a continuous supply of fuel to the combustion area, that is, the area beneath the shell. Heat from the flame satisfies the second requirement for steam production. As the shell heats up, heat is transferred from the shell to the water, and the water boils, producing steam. But a boiler modeled on this example won't work for industrial applications. First of all, the shell is open to the atmosphere, so there's no way to collect the steam. In addition, as the water boils to steam, there's no way to replenish it. Without water, the shell could overheat and be damaged. Given these factors, we'll have to make some changes. First, we'll cover the shell to prevent the steam from escaping. Then we'll add a steam outlet line to collect the steam and route it to where it can be used. We also need a way to supply water to the shell so it won't boil dry. So we'll add a feed water line. It will provide a continuous supply of water to replace the water that's changed to steam. Now we have a boiler that can heat water, produce steam, and route it out of the shell to where it's required. But this design is still not as efficient as it could be. Can you think of a reason why not? With this design, much of the heat in the combustion area escapes to the atmosphere. This heat is wasted because it doesn't go toward the production of steam. This boiler can be modified further to make it more efficient. By adding an insulated casing, we can minimize the heat loss, but this creates another problem. The flame goes out because the casing cuts off the source of air. To correct this, we'll add a fan to supply air to the boiler and an outlet to remove combustion gases. Although this design is still greatly simplified, now we at least have a boiler that provides a constant supply of steam efficiently. In this topic, we saw the basic requirements for steam production and combustion. We also put together a simple boiler that operates to meet these requirements and produce steam. Heat transfer is a natural process that occurs anytime there's a difference in temperature. Heat naturally transfers from a hotter object to a colder object. Basically, heat transfer occurs in three ways: radiation, convection, and conduction. Radiation is a process in which heat is transferred through electromagnetic waves. All matter gives off some radiant energy in the form of electromagnetic waves. But the best example is probably the sun. It gives off vast amounts of radiant energy. As the sun's radiant energy travels through space, some of the electromagnetic waves contact the Earth. Some of these waves are reflected back into space, but others are absorbed by the Earth. Only the waves that travel in a direct line of sight between the Earth and the Sun come into contact with the Earth. The energy contained in the waves is absorbed by the Earth as heat that warms the Earth. The amount of heat transferred depends on the number of electromagnetic waves absorbed. A second type of heat transfer is convection. Convection is the transfer of heat within a fluid, that is, a liquid or a gas. It's caused by a mixing action within the fluid. To demonstrate convection, we filled a beaker with water and set it on a hot plate. We'll also add some dye to show the mixing action. As the bottom of the beaker heats up, the temperature of the water closest to the bottom increases. As the temperature increases, the water becomes lighter or less dense, so it flows upward. The warmer water mixes with the cooler water near the top of the beaker, and heat transfer occurs. This type of heat transfer is known as free or natural convection because the movement of the fluid occurs naturally. Convection heat transfer that's produced mechanically is called forced convection. Many buildings have forced convection heating systems. These systems use fans to force warm air into rooms. The warm air then mixes with the cooler air in the room, and convection heat transfer occurs. A third type of heat transfer is conduction. Conduction is the transfer of heat through a solid object or between two objects as a result of physical contact. For example, if we heat the middle of a steel rod, the end will heat up as well. The heat transfer from one end of the rod to the other is due to conduction. We've now seen the principles behind radiation, convection, and conduction. Each of these types is involved in transferring heat from the burning fuel to the water in a boiler. To see how, we'll use this example. This type of boiler is called a water tube boiler, but the heat transfer principles at work apply to just about all boilers. The boiler has a series of tubes and two drums which distribute water to the tubes. The tubes form a wall around the combustion area. This is the area where heat is generated. When fuel burns in a boiler, radiant energy in the form of electromagnetic waves is produced. These waves travel through the combustion area. The waves in a direct line of sight with the tubes make contact with the outer tube surfaces, and the tubes absorb heat. This is radiant heat transfer. The burning fuel also produces combustion gases. As these hot gases pass through the boiler, they transfer heat to the tubes as well. This is convection heat transfer. As the outer surfaces of the tubes absorb heat, conduction heat transfer occurs. Heat is transferred from the outer surface to the cooler inner surface. Then heat is transferred from the inner surface to the water flowing through the tube. Convection heat transfer also occurs as the warmer water mixes with cooler water. When enough heat has been transferred to raise the water temperature to the boiling point, steam is produced.